Welcome to Fun with Science, Engineering, and Technology. My name is Mr. Ross. Today we're going to do a follow-on with a little bit more about sound. Right, my acoustical engineers this morning are
Jason and Julio.
Jason and Julio. Right. Some of you may have seen the previous show where we went through and did some basic stuff on sound. Right. We had two other acoustical engineers with us at the time. But basically what sound is, all right, is compression of the air and expansion of the air as we talk. The reason the sound waves are getting from me down into the microphone are because my vocal cords are vibrating and generating the sound waves, right? What they're doing is they're squeezing the air together. When the vocal cord vibrates this way, it compresses the air, squeezes all those air particles together, right? And then they expand when the vocal cord goes the other way, right? Or they rarefy, as they call it. Right, so we compress it, expand, right? And that's how the sound waves get to you, right? They don't get to you instantly. They're traveling at somewhere around 345 meters per second, right? So it's pretty quick, but it's not instantaneous, right? So, now, Julio, what I want you to do is to get down here. We'll show a little demonstration. Get down and pick up one end of this. What is this? Giant slinky, right? Like a big spring. Okay. So what we can do is we can use this to demonstrate what I'm talking about. Right. All you need to do right now is just hold on your end. Right. Don't let go of it, because you're going to hit me with it. Right. What I'm going to do is I'm going to squeeze it together like this. Right. So that I've squeezed all the little coils of the spring together, and I'm going to let go of it. Watch it very carefully. What happened?
It went like that.
It went back and forth, right? Where I'm compressing, squeezing these together, and I let go of them. When I let go of them, that compression, right, is going to travel down the spring. It's going to hit you, your hand, and it's going to bounce off and come back. Do it again. Right? That's what sound waves do. When we're talking in here and I'm speaking, sound waves are going, compressing the air, right, and then it expands, compresses, expands. It goes, it hits the wall, and guess what it does when it hits the wall? It comes back. That's why when you go out in the schoolyard and play, right, and you shout at the building, which everybody shouts at a building, right? You get an echo back if you're at the right distance, right? This is called a longitudinal wave, right, because that compression is traveling the same direction as the wave is traveling, sound is traveling along the spring. Now, there's another kind of a wave. Hold on very tight, because I'm going to do something else, right? Which is called a transverse wave, where it goes up and down. It's traveling in this direction, but the wave is going up and down like this. Okay, so, right, if you look at it now, right, what's happening? Right,
It's going faster.
it's going faster, and if I go, let me get it again. Right, we can make it even go even faster, right?
Mm-hmm.
Right, let's put that down. Now, let's take a look at the little chart I have here. What we have is that last one we did was a transverse wave. And if we looked at it and we got it going just right, it would look something like this, right? It would go up, start down here, go up to what's called the crest, right? Go back down to a low point, which is called the trough, right? And then back up. The longitudinal wave, where we have the spring squeezed together here, right? And it travels along, right? Here it comes, gets wider apart, right? Which, like the air molecules, when we're talking or generating sound, right, the air molecules are squeezing together, then they're spreading apart and squeezing together and spreading apart, and that travels down, right? Then we have a compression, then we have a rarefication here, right, and another compression. Now those compressions of that coil, right, correspond with the crest on the wave, right? Where we get a rarefication corresponds with the trough, right?
Mm-hmm.
Now, during the last show, what we did is we measured the wavelength. There's a distance between those. Right? We look at this, right? Here is that transverse wave that we have. And when we pick two points, the same point up here at the crest to here, right, there's a distance between them, right? And that distance is the wavelength. Same with the sound waves, right? Where it's compressed here and over here, right, there's a distance between those, and that's also called the wavelength. It's how long those waves are. Right? So we have wavelength, right, between here and here. And if we also have another one, which is called amplitude, or how loud the sound would be. I mean, I can talk real soft like this, or I can talk real loud, right? And that is the distance between here and here, right? The louder it would be, the more this would be bigger, right? And the more compression we would get, and the more rarefication we would get on the sound wave. Okay? Frequency is how fast it goes up and down, right? So if we take this, like this, right? And if we look at the two waves, the transverse wave and the longitudinal wave again, the frequency is how many of these waves pass a given point at one time. So if you were able to be standing here and looking at them, right, and you pick a spot and then the waves go by, if you counted them, is how many go by in a second would be the frequency. If there's 100 of them going by in a second, the frequency would be 100 cycles per second, or 100, but they have another name for it called hertz, be 100 hertz per second. In this particular case, this time is 1 second, so it's 1 hertz, or 1 cycle per second. Down here, this waveform, right, how many we got in there?
3.
3. So what do you think the frequency is going to be?
3 hertz.
Be 3 hertz, or
3 cycles.
three cycles per second, right? This frequency is twice or 3 times this one up here. If there were 100 of these in here in a second, what would be the frequency?
3 hertz or 3 cycles.
No, 100.
100, oh yeah.
Yeah,
right.
but this is 3. If we do 100,
100 hertz.
be 100 hertz, right? Or 100 cycles per second. Let's do another one. Right, here's our big slinky squeezing together, spreading apart, squeezing together and spreading apart, right? And these up here represent the molecules in the air, the particles in the air. Where it's squeezed together, there's a whole bunch of them. It's pretty dense, right? Then it's where they spread apart, or we get rarefication, there's fewer molecules together in there, right? More molecules, fewer molecules, more molecules. Now, the more molecules we squeeze together, the higher the air pressure, right? Where we have fewer molecules in a given space, the lower the air pressure. So what happens is then, as the sound wave comes past and goes past your ear, right, we get high pressure and low pressure, high pressure, low pressure. Inside your ear, there's a little diaphragm, right, that is able to move back and forth like this. Where it's high pressure, it pushes in on it. Low pressure, it allows it to come back out. So it sits there and goes like this. That in turn moves those little bones in your ear, which stimulates some nerves, right? Causes your brain to say, huh, Mr. Ross is talking to me. And sometimes he's funny and sometimes he's not, right? So, and your brain interprets all that and lets you understand what I'm saying. So, again, what we have is where our slinkies squeeze together, we have what? High pressure, right? Where it spreads apart, we have low pressure, right? And that's what's happening. If we could see the molecules in the air, that's what we would see. We'd see little bunches, density of them, right? Bunches going, then they spread apart, bunches, spread apart, bunches, and that would be the sound wave going through the air. And that happens at 345 feet per second as it travels, right? Now, the amplitude, how loud it is depends upon how tight these things are squeezed together, these particles, and how far apart they spread, right? How high the amplitude, how high the pressure is, and how low the pressure is. The difference between the crest and a trough, if you will, on this, right? This is the amplitude. No. So we have sound, we have the speed that it travels, we have its wavelength, we have its frequency, how often it vibrates up and down, right? Those waveforms go up and down. And we also have amplitude, how loud, how intense the sound is. And when you're in the classroom, the amplitude gets pretty high sometimes, right? Sometimes it's pretty low. No. So we need to measure that amplitude. Right? That's what we're going to do today. We're going to measure the amplitude. And the amplitude is measured in a unit called decibels. Never heard that one before, I know, right? Or dB. Right? And if we take a look at it, the threshold of hearing, if you get sound level down so low, right, your ear won't be able to detect it, right? And as soon as you creep up the sound amplitude, the energy in the sound creeps up just above that. This is called the threshold of hearing, and that's where you start hearing. You can tell there's a sound there, right? And that is called 0 dB. That's the baseline. That's where we start from. Okay. Leaves rustling, right? The wind's blowing, nice quiet day, you're out in the woods, and you get a little, you can hear the leaves rustling around, right? Not very loud, is it? That's 10 dB. Right? Conversation, normal conversation that we're having like right now, it's about 60 dB. Now these are all average numbers. They're not hard, fast rules because some conversations are louder than others. If the wind's blowing real hard, right, the leaves rustling may be a little bit louder, right? If it's in the fall when the leaves are all dry, they're going to rustle a little bit louder than they are in the springtime when they're got a lot of moisture in them. Right. Now here's an interesting one. Rock concert is 110 dB. A lot louder than leaves rustling. 110 dB. Right below it, 120 dB, is the pain threshold. Just go up just a little bit from a rock concert, and the sound energy is so strong it can cause pain in your ear. Right. Once you start having pain in your ear, what's going to happen next? It could cause damage to your ear, right? And cause you to lose hearing. Rock concerts, if you sit all day long and listen to a rock concert, even though there's no pain, you can still get some ear damage. Jet engine, right? It's 130 dB. That's way above the pain threshold. And if you ever get on an airplane and you see the guys out there on the ramp when the plane starts up and they're out there working, doing whatever they're doing, you'll see that they have things on like headsets, right? And what those are for is to block out the sound, right, from that jet engine when it starts up, because they don't, right, they're certainly going to get some hearing loss and some damage to the ear, which is not a good idea. Now, do I sound like you?
No.
I certainly don't sound like him. No, right? And you, the two of you don't sound like. If we brought one of the girls in here and had her talk to us, they sounded completely different. Why?
Because they have a high-pitched voice.
They have a high-pitched voice, higher frequency, right? But if I take two girls with higher pitched voice and I stand them side by side, do they sound alike?
No.
No. They don't sound exactly alike, right? And if I play a piano, hit a C note on a piano, pluck the C string on a guitar, do they sound alike? Play a C note on the trumpet, they don't sound alike either. And the reason for that is that your voice is made up of one set of sound frequencies. Your voice is made up of another set of sound frequencies, right, which is a little bit different. Mine is different, right? The girls will be different. Piano is different, so all the sounds sound like, because when we speak or when we play the piano, whatever we do, we don't generate one frequency. Like this tuning fork that I have, right? That's one frequency. We don't sound like that. If we did, we'd be a little hard to understand. Okay, so different sounds are made up of a whole bunch of different frequencies. As an example, we take a motorcycle, right, and this is the graph chart of the sound frequencies. On the vertical, we have the intensity or the pressure levels or the loudness, right? Along the horizontal line, we have the frequency in hertz, right? Down here is 0 frequency, 200, 0 hertz, 200 hertz, 400 hertz, and so forth. If you look at this chart, right, what is it showing us? Down on these low frequencies, this motorcycle, the frequencies that it generates as it's running down the road, right, are much higher than they are up at the higher frequencies. Right? Take an automobile, right, and it has different sound on the motorcycle. Right? So the chart for the motor vehicle is going to look a little bit different, right? Because it has a different set of frequencies. Motorcycle manufacturers, I mean, you don't want to get on a Harley and have go, right? You want to be big. So what they do especially the Harley Davidson motorcycles, they have some acoustical engineers that sit around and make sure those things sound like that's a Harley should sound, right? And that's part of their sales pitches. You know, you walk into a motorcycle shop and fire this thing up, boom, 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 boom. It sounds like a Harley, right? So all of us have a little bit different frequency in our voices, a different set of frequencies. Now, to complicate matters even further, right? Our ear, doesn't respond to all these frequencies equally, right? Normal hearing, range of hearing, and this is an average, right? It may not apply to you, may not apply to you. Certainly doesn't apply to me because I'm too old, right? Normal range of hearing is you can hear from 20 cycles all the way up to 20,000 cycles. That's where human beings can hear, right? But we don't hear all those sounds, all those frequencies, right, at the same level. Our ear doesn't respond to them all exactly the same, right? And it varies from person to person. And and as you get older, the high frequencies I can't hear anymore, right? Used to be I could hear something like 18,000 cycles per second. I can't hear those real high frequencies now because my ears have deteriorated a little bit. But if we take that chart and we plot it, the guy in his ear, right? Again, we have sensitivity in dB, right? How sensitive your ear is, how much it's able to handle, right? And along the bottom we have the frequency. This chart only goes up to 10,000, but it could go all the way up to like 20,000. And basically down at the real low frequencies, your ear is not very sensitive. As we get up into the around 2, 3, 5,000, right? The ear can hear those much better. It gets more sensitive. As we start on all the way up, it starts to drop back down again. So, if I were over here and I have 20 cycles per second and boom, boom, your ear doesn't hear that very good. Can't pick those up. If I get up 2,000 cycles or 1,000 cycles, right, then your ear is more sensitive to that. You can hear that better, right? I get up to 20,000 cycles, you may not be able to hear at all. If you do, it's going to be very, very, very small as far as your brain is concerned. Okay, so now, how can we measure that loudness? Right. I happen to have a thing called sound level meter. Right. The sound level, there are all kinds of sound level meters. This is a pretty good one, right? What it has up here on the top is a little microphone, right? It has a digital display down here, right? There are some other switches and so forth on it. One over here is was labeled A and C. Now, what they want to try to do with this sound level meter, right, because it's measuring the sounds that we hear, right? They try to make it act like the human ear, right? So if we Up in the A position, it sort of corresponds to this. Down at the very, very low frequencies, right, it doesn't respond to them very good. As we get up into the middle range, 2, 3, 4, 5,000, right, it gets more responsive. As it gets up to the real high frequencies, it starts to drop down a little bit. So this is, like I say, is to measure the sound levels. Right now, and it measures it in dB. Right now, it's registering 72, 74 decibels, which is the background sound level in this room. Right? A couple of interesting things about this is what do you think that's for? What is it?
Sorry for the microphone.
It's for the microphone, right? Because if I take this outside and the wind's blowing, right, the wind's going to blow across this microphone. It's going to cause some noise, right? So what we do is we do a little foam rubber ball over it, right, which causes the wind not to create that noise. It's like a windscreen, right? So now then the wind can blow across here, and we're going to noise. You don't have all that noise generated by the wind, right? The sound can still get through this ball, right? When I'm talking to it, right, it's registering the dB from my voice. I don't know if you noticed last night on the Grammys, some of the singers up in front of the microphone, right? They had a thingy in between them and the mic, right? A little round disc affair, which is basically a little netting kind of a thing. And what it is, because if you get a microphone and you get up here and you start talking at it and you're real close to the mic, right, you're going to get puffs of air coming out of your mouth, right, which is going to hit the mic and cause the microphone to pop a little bit. So what they do is they put a screen in between the singer, right, and the microphone, and that blocks that air, but it lets the sound go through. And this is the same kind of arrangement. We're going to take it off because we don't need it in here. No. You may have heard that the police department goes around with a sound meter and checks the cars for loud stereo music, right, and writes up tickets. Well, this is what they use. The sound level meter. In fact, this one belongs to the police department.
You took it from them?
I borrowed it. I didn't take it from them. They loaned it to me. Right? So, now if we're going to go out, we're going to issue a guy a ticket. Right? We want to make sure this thing works right. How do we do that?
Test it?
Test it, right. Not only is it tested, but it's also calibrated. What we do is we have this gadget, right, which is a little calibrator, right? What do you think it should do? It should generate some sound. Turn it on. You hear it?
Mm-hmm.
Right? And if we take and we put it over top of the microphone like this, right? And the amount of sound coming out of there is like 114 dB at that distance. So this should read 114 dB. Does it?
Yeah.
114.0000, and sometimes it's 1, but 114 dB. Now, if it didn't, what it would do is right up here is a little tiny screwdriver adjustment where I can adjust it. How do I know this thing is right? How do I know that this generates 114 dB of sound? You don't know? Well, what we do is we calibrate this. Right? This is sent off to a calibration lab. Right? Metrology, big word, metrology lab. It's a calibration lab where they have all kinds of test instruments. Once a year, this part, the meter itself, and the little calibration unit are sent off to this lab, right? And where they test this and make sure that it's putting out 114 dB of sound at 1,000 cycles, and they make sure that this thing sort of is all up to speed and running right, and approximates the response of your ear, right? That curve that we had here. Right? So they calibrate this. And that, on this particular one, it has to be done once a year. And if we look at it, there's a little calibration sticker. When's the calibration due? Does it say?
March 2004.
March 2004. So this one's about out of calibration. It needs to be sent off to the calibration lab. It says there's guys on there, metrologist, which is the calibration guy. That's the guy that did it the last time.
Douglas Warden.
Good, Douglas Warden. Right? So we know exactly who did this the last time. So if it's not right, we go back to him and say, Douglas, you messed up when you calibrated this. All test equipment, right? Like over at Raytheon, where they build the guided missiles and so forth, and all the test equipment, right, has to be calibrated. Right? It has to go off to a calibration lab or a metrology lab to be calibrated, so that when they go in and they test something, they know that it's right. Right? This is once a year. Some of that equipment, right, and some of the equipment that NASA uses has to be tested like every 30 days, some of it every 90 days, right? Some of it every 6 months, some of it maybe never, right? But it depends upon the kind of equipment we have and what we're going to use it for. Right? So I'm going to put the calibration unit back. We're going to assume that it's all calibrated and so forth. Put this out of our way. What do you have over there?
Which one? This one or this one?
Either one.
It records your voice. A radio station.
Radio, right? We're not picking up very good in here, but because we have a lot of interference. That's all right. Now, I take my sound meter, okay, and I've got my radio playing. I've got it on, and I start out here, and I'm 20 centimeters from the radio. And what's it read?
Like 70 to 80.
Like 70, 71, right? On average, right? Okay, it's like 68.
Yeah.
68 point, whatever. 73. Now, it's 20 centimeters from the radio. I'm going to take and I'm going to move it back over here to 40 centimeters from the radio. And let's see what happens.
$65
So it went from like 70,
to 60 drop.
it dropped, right? About how much?
Like 10, 9.
6. About 6, wasn't it? Let's go back up here. We're to 20. Let's do it again. Right, it's 67.7, right? 75. That's because I'm talking. Let me be quiet. $67.6, right? Just remember that. Move it back over here to 40. And what happened to it? It went down to 60.
4.
If I don't talk, it's down to 64. Right? So what happened is further away we got. What happened to the sound level? Up here it was 70 something, right?
It dropped.
Down here it's 60 something, so it dropped. If I get further away, what do you think is going to happen?
It's gonna drop even more.
It's even going to drop even more, right? And it's like if I get further away from you, if I go outside and talk to you like I'm talking, right, the sound level goes down, right? If I get closer to you, right, get up really close, and what happens to it?
It goes up.
It goes up, right? And the rule is if I'm sitting here and it reads
30.
if I'm setting on 30 and I get a reading, right? If I go a little bit closer, it's going to get louder. If I go further away, it's going to get lower, right? Now, what do you think is going to happen if I, what was this one again? About 68, 69, right? And I'm not talking. I'm going to turn this radio off. I'm going to turn this one on. And what I'm going to do is I'm going to adjust it. To where it's up there about 63, right? Now, so this one's on, that one's off. What do you think is going to happen if I turn the other one off? This one was, they got to add together, huh?
The sound is going to add together and that's going to get louder.
Okay, so this one is 60 something, that was, what, 60 something also? So we're going to get 60 plus 60, which will be 120, you think?
Not 120, but it's
Somewhere
going to get
close
louder.
there, right? We're doing an estimate, right? What did it do?
It's going up there.
But did it go, how far up did it go?
Like a few.
Just a few, right? Just, all right. The reason for that is because when we measure in decibels, right, that we had before, going back to our decibel level, right, every 3 decibels, every 3 dB that we increase, right, we double the sound, the intensity, the energy coming out of it. Right? So I have these 2 radios set up exactly the same, right? So that one, let's say 70 dB, and this one's 70 dB, and I turn them both on. Right? What have I done? I've doubled the sound energy. So it doesn't go up to 140 dB, it goes up to 73 dB, right? Because every 3 dB doubles, right? So like if I go from 0, the threshold here, up to 10 dB, which is the rustling of leaves, that's about how many 3s? It's about 3 times. So what would it be? 2 times, right? Then 2 times 2 is 4, and 2 times 4 is 8. So this is really about 8 times louder than the threshold of hearing. Okay? So, we can look at that on this chart. Let's turn this off. We don't need all that extra noise. Right? And if I have 2 cars, right, and this one's putting out 80 dB of noise, right, and this car is putting out 80 dB of noise, and I add them together, what do I get?
83 dB.
I get 83 dB because I've doubled the sound, right? I've doubled the intensity. This one's putting out certain intensity, this is putting out certain intensity, I add them together and I double it, it goes to 83 dB. Right, so it doesn't go to 160, it only goes to 83. Every 3 dB, the sound intensity doubles. Right? Let's do another little comparison chart. I take one car that's putting out 80 dB, right? Then I go to 2 cars, which we just showed was 83 dB. I go to 4 cars, right? That's twice the sound is being generated by these 2, right? And it goes to what?
86 dB.
86, so it went up another 3 dB. Right, and then I go over here and I get 8 cars, which is twice this, right? And it only goes up another 3 dB, so it went from 86 to 89 dB. So those 8 cars there would be the same as having just 1 car that generated 89 dB. You're looking at me like, you understand that?
Yeah.
Okay. So it doesn't add like you do in your math class where the 80 plus 80 is 160, but it goes by up by 3. Every time you increase the number of dB by 3, you double the sound. Now, the other thing that we were doing was we're moving back and forth the meter, right? And as we got closer, we got more dB. We got further away, we got less dB because the sound intensity was higher when we got closer, right? If you take, and one of the things I want to point out before we go any further is if you take my little calibrator, all right, this puts out 1,000 cycles and 114 dB if I have the thing in here. How loud is that? Is that very loud?
No.
It's not very loud at all. It's sort of like if you had a pair of headset laying down here, and you had your boombox hooked up to it, and it was laying there, it's almost as loud, right? So if you take this and you put it up and you slap it to your ear, guess what?
Louder.
It's louder, and this thing gives you 114 dB right here. How far do I have to go to get the threshold of pain?
Pretty far.
120 dB, not very far, right? So if I crank this up a little bit, right, like some of the boom boxes are able to do, right, I could get some ear damage if I wear those headsets and listen to all that bebop and music that you guys listen to. Right. Pretty soon you'll be like me, you can't hear it. No. All right, so the way this works is every time we double the distance from the sound source, we decrease the sound level by 6 dB. In other words, it's cut in half, and it's cut in half again, right? Because if we decrease it only by 3 dB, we cut the sound level in half. If we decrease it by 6 dB, we cut it down by 1/4. So if you look at our Harley Davidson here again, tailpipe, right? And if we're 10 feet away and we have 84 dB, if we double that and we go to 20 feet away, right, we drop down 6 dB from this 84 and we have 78 dB. The level drops off that way. If we go closer, we go half of this, we're at 10, we have 84, and we go closer, we go down to 5 feet, what happens to it? See it?
It goes higher.
It goes higher. What did it go? It jumped up how many dB from here? 6 dB. So every time we double the distance or halve the distance, the sound level changes by 6 dB, which would be 1 dB would be 2 times, right? Another dB would be 2 times 2, which would be 4. So the intensity changes by 4 or more, right? So it's 4 times louder here than what it is here. It's only 1/4 as loud here as it is here at those distances. All right? So, what we've done today is we went back and we looked at the different waves that we had. We had the longitudinal waves, which is what sound waves are, where we're compressing the air together and we're expanding it, and where it's compressed together, the pressure is higher, whereas expanded, the pressure is lower, and that's what's coming across our ears to give us the sound, right? Because it's causing the little diaphragm in your ear to wiggle back and forth, sort of like this piece of paper, right? Which stimulates those bones, stimulates the nerves on the inside, and causes your brain to say, ah, it's talking to me. The other thing that we learned was our ears are not linear, right? They respond to lower sounds less than they respond to middle range sounds, and they respond to high range, high frequency sounds even less, right? So if down at 20 cycles, the lower end of our range of hearing, right, they don't respond very good, our ears don't, right? We get up into the middle range, around 5, 6, 7,000 cycles per second or hertz, right? The ear responds much better. We get up to the 20,000 cycles per second or 20,000 hertz, right? And the response drops off. We don't hear as good. Okay. We take two sound sources, right? Our two radios there, or two cars, whatever. If they're equal and we add them together, right? If that was 70 dB and that's 70 dB and we add them together, what do we get?
73 dB.
73 dB, right? Because every 3 dB is a doubling of the sound intensity. All right, if we move away from the sound source, it gets what, lower?
Mm-hmm.
We move closer to it,
It gets higher.
it gets higher. So if we were sitting here at 30 centimeters from the sound source, right, and we move out to 60, right, it's going to get lower, and it should get lower by 6 dB. If we're at 30 and we move into 15, it's going to get louder, and it should get louder by 6 dB. Right? So that's it for today, with the sound. We hope you enjoyed it, and come back the next time, and what we're going to do is we're going to look at some ancient footprints.